Okay, today I don't know if I'll be able to do the tablet because tablet is not working. So what we'll do is we'll use a chalkboard today, and we'll do a clicker question on my other computer, which is up there. My tablet computer is very quirky, and I left the power plug out Wednesday night after class, and its battery ran down. And on these old Macs, it's a blinky green light. It won't turn on until green blinky light goes away, and I didn't notice it until before class, so it's kind of a shame. But we can probably use a chalkboard. We can go old school today. And Beatrice, luckily, is my chalkboard eraser. So anyway, what I was going to talk about first is ecotoxicity, and then we're going to do a little thermodynamics review, probably, or overview, depending on whether you're taking Chem 1A concurrently or you already took it. I don't know where you guys are in that class. I guess you've already done a fair amount of thermodynamics. Wow, it's hard to erase, eh? All right, well, that's okay. I can just go ahead and... How many boards do we have here? Start with what? This one? I see. Got it. All right, so we're going to do ecotoxicity. I hope you can see this. Okay, and what I was thinking of doing here is an example for you. There's, I guess, still some questions about how you do these ecotoxicity experiments. And imagine I was doing the following experiment. Okay, and in this experiment there were, say, 10 subjects. 10 subjects per dose, okay? Can we all kind of calm down? I know it's kind of noisy. It's 10 subjects per dose, okay? And the other thing that we have is the average weight of 2 kilogram weight per subject, okay? These are key parameters. And the question is, given some data, what is the LD50? Okay. So now I'm going to go ahead and put this board up and give you some data. Hopefully it won't disappear. It's magic. And okay, so now we have a table, some table of data. And we have dose here, and then we have number of survivors. Okay, so units on dose. In this case, we use micrograms. That's a little mu, Greek mu, micrograms. And we'll imagine some doses here: 1, 3, 10, 30, 100. Okay, and then of course when the dose is low, and now we're measuring number of survivors. All of our survivors in that trial survived. Okay, so 10 survivors. And then as the dose increased, at 3 micrograms, we lost one of the 10. And somewhere here around, say, in the middle of this series of doses, we saw about half the survivors. Say one survivor made it when the dose was 30, and then no one survived. No one survived when the dose was high, was 100. Okay, so that's more or less what you'd expect to see in some kind of model data. And right away, you should be able to look at this and say, okay, this condition here is going to be the condition where 50% of the survivors, 50% survived. Okay, because 5 over 10 is 50%, right? So now we need to just do a little bit more math to figure out what the dose, because we want to figure out the LD50 in units of, say, micrograms per kilogram weight of survivor. So that's pretty straightforward. So we have our LD50 value that we want to compute, and we have this information. We have 10 micrograms of our dose here, whatever, our toxin, whatever it is. And then we have the weight of the subject, which was 2 kilograms, okay, of the subject. So it's a pretty simple factor labeling. You're just going to end up with 5 microgram dose per kilogram of subject. Okay, so I hope everyone has perspective and they can see this. But remember that my notes will be uploaded, the electronic version I did on Wednesday, minimally. I could even scan these hand notes here as well. I have a scan of these. All right, so that's your basic LD50 experiment. And now we wanted to just do a little thermodynamic introduction because, we want to do a little thermodynamic introduction because, of course, once you've made your biofuel and you've tested its ecotoxicity and so forth and so on, then you're going to ignite or burn some biofuel in a special burner and then collect all the heat in a makeshift calorimeter and then determine, thermodynamically, its enthalpy of combustion, okay? And so that's an important parameter to know how much heat energy is stored in, say, a mole of this particular fuel to show that it's energy dense and useful for, say, operating heavy machinery, like some diesel-powered machinery. So I thought I would just give kind of an interesting example to start out with, and I wanted everyone to imagine something that you have a lot of sense of already, ice, and sort of the scale for how much energy is stored in frozen ice. Shameless, calling me during class. All right, so here's a big cube of ice here that you're going to imagine. All right, this is a cube of ice. All right, and this is a huge cube of ice. This is a meter on all sides, okay? Does anybody know how big that would be? Somebody said it. Who said it? Cheater. All right, no one answered the first class, but of course someone downloaded the notes from Wednesday. And anyway, a meter cubed, of course, that's not so interesting or easy to think about, but when we have 100 centimeters cubed, we end up with 1 times 10 to the 6 cc's, cubic centimeters, or 1 times 10 to the 6 milliliters, right? And if we divide that by 1,000, we end up with 1,000 liters, and we know there's a kilogram per liter for water, the density of water being 1 gram per cc. So that's going to be 1 times 10 to the 3rd kilogram of ice. That's a metric ton. That's a lot. It's kind of surprising. I don't know. I think that we sort of don't have a good sense of scale, so that's why I'm doing this. So now the question is, there's a lot of you in here. I can already feel the heat. Well, actually, the lights are shining on me, but I can already feel all the body heat in here. And what I said to the Wednesday class was, is anybody here? I know I've already asked you about alcohol consumption. Have I? Oh, maybe. We're talking about toxicity. So that's why you need to normalize the body weight. But the other thing about I asked the other class was, has anyone been to a fraternity or sorority party? Anyone? No. This is weird. 2 classes. I have over 750 students, and no one's been. I think I've been to more fraternity parties while I've been at Berkeley than the undergrads. No, I'm just kidding. I've been to 0. All right. So me neither. So this is not going to be a very interesting analogy, but what I'm ultimately getting at, since no one's been to a party, is that when you're in a small room with a lot of people, what tends to happen, the body heat starts to build up. You start to really actually feel almost uncomfortably warm, unless you've had some alcohol to drink and you don't really notice. So the question is, how much heat does a student yield? What's a student's power? Do you know what a student's power is? Does anybody know? How much heat are you evolving per second? That's what power is. It's around, if you calculate the average caloric intake and so forth and so on, it's about 100 joules per second or 100 watts. So everyone is a 100-watt light bulb, okay? Isn't that phenomenal? You can't buy 100-watt light bulbs anymore, but you're about a 100-watt light bulb. So the question is how many students is it going to take to melt a cubic meter of ice? And I'm assuming there's like 300 or 400 of you guys here. And to keep things easy, I'm going to just assume there's about 334 students. Now, it's a funny number, but it does agree quite nicely with the heat of fusion of ice. So to understand how ice melts, we're going from frozen ice to melted ice, we need to consider a thermodynamic parameter called the heat of fusion, okay? And I'm going to write this out in these heat of fusion units as a specific heat of fusion in terms of kilograms and kilojoules. And it turns out that actually is also 334 kilojoules per kilogram, okay? So each kilogram of ice is going to take 334 kilojoules. I say there's 334 students, but there's metric ton of ice. How long is this going to take? And I've already screwed up these boards, but see, look at that. My left hand is even getting exercise today. All right. No, I didn't mean that. I mean, God. All right. I walked into that, but I didn't mean to. I didn't really. All right, boy. I'm supposed to be making you embarrassed. With my fraternity and alcohol jokes. All right, so now we have a heat of fusion. Sorry, I want to change this here. So we want to figure out, how much enthalpy is it going to take to go from ice to water, okay, to liquid water. So we got solid ice here to liquid water, and we just need to multiply this heat of fusion 334 kilojoules per kilogram times 1,000 kilograms, and so we're going to end up with 3.34 times 10 to the 5th kJ. Okay, and so then you basically have to do the factor labeling here. 334 times 10 to the 5th kilojoules, and then each student, we say 334 students, and students are producing 0.1 kilojoules per second. And so now I will have figured out how long it will take to melt that ice. And you can do the math here. You'll end up with 1 times 10 to the 4th seconds. Does anybody know how many seconds are in an hour? 60 times 60, 3,600 seconds. So that's about 2.8 hours. Okay. So that'd be pretty cool. If we had a cubic meter of ice, we distributed, every one of you would get 3 liters of ice, and it was still, you couldn't do it in the period. Do you think that's true? Do you guys think that's true? You guys think you could melt 3 liters of ice and just kind of curl over it? It'd be painful. I mean, I estimate probably, if you really cranked up your metabolism, for example, you go outside with not very many clothes on, and it's really cold out, your body's thermostat's going to go up. But I only estimate about 30% of your total energy expenditure could really go into that ice melting process. So probably take a lot longer than 3 hours. Maybe you could put more, say 50%. It would take you quite a while to thaw all that, if only your body heat was going into it, not the heat of the room itself. So, and that's the assumption. But what I like about this sort of thing is that it gives you a sense of how much energy goes into even something as simple as ice melting. So now, all right, so I'm getting, this is a good setup. Oh, good. Okay, I don't understand chalkboard technology yet. All right, so that is melting ice, and the other important sort of thermodynamic tidbit that you're going to need for your lab is of course just regular old plain heating of water. You're not really going to be doing any ice experiments, although they would be quite illustrative if you did. But when you're heating water, you're going to use this equation or a version of this equation, and everyone should be pretty comfortable with these terms. This is again this is the enthalpy, and it's synonymous in this particular case with heat, which people like to do like this, Q, and then we have the heat capacity. So we have an enthalpy. We'll get units here of, say, joules or kilojoules, something like that. And then we'll have, say, heat capacity. Let's just do it in joules. Shouldn't have done that. And then we'll have a heat capacity generally for water in units of joules per mole Kelvin. Okay, joules per mole Kelvin. And you can see that I have a temperature here. This is heat capacity. And I have a temperature here. This is your temperature. And then I have here some number of moles. All right. So you can see in order to get units of joules, I need to multiply by moles of substance and temperature. So what's heat capacity? Heat capacity can be a rather abstract concept that's hard to understand, but essentially if you have a glass of water, it has all these water molecules in it, and these water molecules have vibrations and rotations and all sorts of ways in which they can store energy. And if those water molecules are storing energy in vibrations and rotations and not in translational modes, then the temperature will not go up, okay? So the more capacity a molecule has to populate different vibrational and rotational modes, the more the greater its heat capacity, okay? So then there's also translational modes as well. So a molecule like water has a heat capacity around 75 joules per mole Kelvin, okay? And So if I had say I had 10 moles of water, I just multiplies. I want to see how much it takes to raise it. Say 10 degrees, it would be 7.5 kilojoules. Okay. And if you did this math for something on that scale, you'd find again that giant meter cube of water there would be a good storage medium for heat. It stores a lot more heat or cooling power as ice than it would for the same mass for say raising it a few degrees. It's sort of hard to compare the two by its heat capacity, but water is a pretty good storage medium, and that's why when you live near the water, it's not as cold as it is living more inland. And the coastal places are slightly warmer because of the buffering from the ocean. All right. So that's sort of basic calorimetry for how what you're going to do in your experiment. You're going to have more or less special wick that goes into, say, a reaction vessel that has your biofuel in it. I don't know exactly how this is going to work. And then you're going to burn it, and it's going to draw the biofuel into this wick and then ignite the biofuel. And then right above that flame, you're going to have some reservoir of water that's at a known temperature, initial temperature, which you have to measure because you need to get delta T. So delta T is going to be equal to T final minus T initial. So you're going to need the temperature before you start your experiment. And then as the biofuel burns and heats up the water, you'll be able to then measure the change in temperature. You should also know exactly how many moles of water you have. So, and then knowing the heat capacity is a given parameter, you'll be able to calculate how much heat was released from a set amount of biofuel. So the question you might have next is, well, what happens when I burn something? So let's burn. I should have burned biodiesel, but I should have looked up its parameters. But I looked up something more familiar to me, and that was glucose. So glucose combustion, which we're all doing right now. That's a major fuel that's burned in your body, generally speaking, unless you're on a very high-fat diet. C6H12O6 is glucose. Plus, if you're going to burn it, you need oxygen. And you're going to produce carbon dioxide and water, just like you will. When you burn biofuel, you're going to do the same thing. So you're going to put biofuel molecular formula here, and you'll use oxygen and so forth. So the way you balance this, people should know, is carbon and then hydrogen and last oxygen. But so the question you'll have is, okay, this is a nice reaction. What is the heat that will be evolved in this combustion reaction per mole of, say, glucose? So we want to know what the delta H of combustion is. Under standard conditions for a mole. So the molar heat of combustion for glucose. And what you do is you use Hess's law, which I hope we know Hess's law, where we're going to basically sum all the stoichiometric coefficients of all the products times their heats of formation. Okay. So and these are for the products. Okay. And then we're going to subtract from that the sum of all the stoichiometric coefficients of the reactants. So stoichiometric coefficients are these guys. And of course, we have an implicit 1 there. So in order to really do this well, you need to know some rules about these delta HF values. Delta HF are, like I say, enthalpies of formation. And so there's rules for these enthalpies of formation. And I'll just state them to you. You can write them down, or you can look at the notes. That if you're a pure molecular substance, for example, oxygen or in hydrogen, or say carbon in the graphite state, then we define for those pure substances. So for pure substances in the low energy state, delta HF naught is defined as 0. Okay. So that makes life easy in this particular case because we have oxygen in this particular combustion reaction. So then we could just basically work out the math. You go to a thermodynamic, you'll go to some sort of table, and in the table you'll have these delta HF values given in some units of, like, say, kilojoule per mole. And so you'll have various things. For example, oxygen, carbon dioxide, water, and glucose. So you'll need all of those guys. What's oxygen? 0, right? Does anybody know carbon dioxide? 393.5. I doubt it. Unless you looked at the notes. And then glucose, water is about 241 kilojoules, and glucose is pretty big. It's 1271 minus. Okay, so then we're gonna light this stuff up. So then we'll figure out our delta H of combustion for glucose under standard conditions, and so that's going to be equal to 6 times minus 393.5 plus 6 times minus 241, and then minus 1271. Okay, adding all that up, we're going to have minus 2536 kilojoules per mole. So this is our delta H. This is our delta H of combustion, okay, for glucose. So it's a big negative number.